Hi, welcome back. So today we will continue with the multiplication law, which is the last part left of your chapter. All right, so let's take a look. So we have multiplication law for independent event. So what is independent event? When one event doesn't affect the other event. Like when I roll a dice. Okay, I like say I roll the dice twice. Doesn't affect, right, whether I get one. Am I going to get one again? No. It's independent, right? Correct or not? Or when you, let's say basically when you toss a dice, you get head or tail. It's independent, right? I may get a head now, I might get a tail later. That's what you call independent. The first and the second event is not related to each other. So this is the first proof that I taught you was mutually exclusive. This would be the other proof that they will always ask you. Prove that the event is mutually exclusive. So when it's mutually exclusive, you will prove that the intersection is 0. When it is independent, you will prove that A intersection B is equal to A times B. Okay, just like what's the probability of getting a head and a head? It means the first toss you get head, the second toss you get head is half times half, right? You've done this before, so just stick to that law. Okay, so let's see, where are we in our manual here? Okay, the way I teach you, I'm just going to teach you this. You don't need to remember this for dependent event, what's going on. No need. Okay, because you will just confuse yourself further. For this, don't worry. When we are doing it, I'll teach you how to do it. If I were you, just remember the independent event formula, and that's good enough. Okay, the key word here is n. So basically, for independent event means you basically things like you replace the marble back, you have the same number of marbles, or you when you take out and you don't put it back, that is dependent. Okay, so I'll go through the questions, then we will look at all this, because if you were to do this, if I explain to you this, you're going to get confused, and I don't want to make you confused. I want it to be as simple as possible. So when I do the questions, actually basically you realize that you're not going to use this part. You just have to remember this when it's independent, but you already know, you're already doing it, like you have done drawing the diagram. Remember, initially we drew this. Okay, I'll just show you. Okay, just like this. How did I get 1/6? 6 and even. Okay, when a single die is tossed, what's the probability of getting 6 and even? These two are dependent. If they are 6, they are so basically even. All right, basically this was what I was looking for. So what is the probability of getting a head and a head? 0.5 times 0.5, right? So head and a head, basically is h intersect h, so that's how you get. So basically you have done this before. This is nothing new. So when it is independent, all right, our probability laws, let's go back there. So basically when it is independent, your intersection will be equal to the multiplication of it. Okay, so you have done this before. Just put this in your mind. When they ask you to prove something is independent, you will prove that the intersection is equal to the multiplication of it. So if both sides are equal, there you have, that's you have proven it. If it's not equal, then it's not independent, it is dependent. All right. Okay, let's look at example 2. A box of chocolates has 30 soft-scented chocolates and 10 hard-scented ones. I ate one chocolate and then the other. So when you have something like that, you pretty much know this is a tree diagram. So if you were to draw it, you need to draw a tree diagram. Calculate the probability that the first was soft and so was the second. So use a suitable sample space. Whenever you have one event leading to another event, let's say you have two events. Okay, we'll just put it here. Let's say you have two events, one leading to the other. This is always tree diagram, understand? All right, but in this case, you don't need, I mean, you can draw, but you don't actually need to draw it, okay? Basically because you can actually already do it directly. In the first pick, you will have 30 out of 40, right? 30 soft-scented chocolates. That means total number of chocolates in that box was 40, correct? So in your first pick, for soft-scented, it will be 30 out of 40 times with the second pick. Now will be 29 because one less ready out of 39. So you had 40, one less is out of 39. So if you can't see this way, just draw the diagram, branch out. Soft-scented, hard-scented. You can just call it SH. Then you branch out again, SH, SH. The way I taught you doing tree diagram the last, same way. Okay, so you will get 29 out of 52. All right. Next example. Two crossword champions work on the same same puzzle. They are sitting in separate rooms. Okay, so if I'm sitting in two separate rooms, what does that tell you? Whatever I do is independent of what the other person does, right? Correct or not? It's independent. You don't know. Basically, I can't copy him. So what he does is independent, is his result. What the other person does is independent. So when it's independent, we come back to this. Okay? When it's independent, we come back to this proof. So I'll just put it here. Okay? So the probability A solves the puzzle. They're giving you the total probability of A is 0.8. They're giving you the total probability of B is 0.9. Use a suitable sample space. Now you have two people. So it's either A solve or A doesn't solve. Or it's either B solve or B doesn't solve. So the only way for you to do this is to draw a two-way table. Okay? So let's take a look. The probability that A solves, meaning the total probability that A solves. So A solve, A don't solve. Total probability of A solve is 0.8. What's the probability A don't solve? 0.2. Total probability must be 1. What is the probability B solve? B solve is 0.9. Total for B. B don't solve must be 0.1. So basically you've got all the outsides, correct? So now, how to find what else you know? What I told you just now, this is independent, right? They're sitting in two separate rooms. But you don't worry, in your exam, it will be a little bit more, they will specify it further. But here, it's because it's an example, they want you to learn through it. Okay, so A and B solve. What I told you, this independent, right? So A and B solve must be the probability of A times with the probability of B, which is 0.72. So once you've got that, you'll be able to fill up the rest. So you fill up the rest first. What's the probability? They both solve the problem, you multiply it. Neither solves. A don't solve, B don't solve, 0.02. At least one of them solve. So whenever you see at least one, the shortest way to do it is 1 minus this. At least one means both solve, either one solve or either one solve. So either you take all three and add up, or just 1 minus, both don't solve. At least one, that will be the shortest way to do it. 1 minus, both don't have. The prime of both. Understand? Okay, so you will get 0.98. So pause as you do it, okay? Understand, then you move on. An Olympic swimmer is to compete in two finals, a 200-meter freestyle and a 100-meter freestyle. The 200-meter is a first event. So when you have first and you have second event, right? This is when you draw a tree diagram. No need to guess anymore. First event, second event is always a tree diagram. Okay, if she wins this event, the probability that she will win is 0.7. But if she loses, so we will do it one by one. Okay, so now the first event is 200. Okay, and she will win is 0.3. So the first event, what's the probability that she will win? She will win is 0.3. So here you need to put 0.3. This will be 0.7. Okay. Okay, what's the probability she lose? So we go back. If she wins this event, the probability that she will win the 100-meter is 0.7. But if she loses, the probability will drop to 0.5. Okay. So now, if she win is 0.3, here will be 0.3, here will be 0.7. I'll complete the diagram. Okay, so I've completed the diagram for you. So the first part, I'll highlight what we are doing, okay? The 200 is the first and the probability that she will win the first event. Okay? The probability that she will win the first event is 0.3. So we go down, first event she will win is 0.3. The probability that she will lose will be 0.7. Total probability 1. So you're on the right track. Next one, if she wins, the probability that she will win the second event is 0.7. So if she wins, the probability that she will win is 0.7. So I'll look at win. If she wins and she win again is 0.7. So she will lose will be 0.3. So total probability is 1, sorted. Now this part is if she lose. So let's find the probability if she lose. But if she loses, the probability will drop to 0.5. So if she loses, it will be a half chance, 0.5, 0.5. So like I told you, you need to complete your tree diagram. You have to write down your outcomes. Winning the first event, winning the second event, winning the first event, losing the second. If you don't want to write L, is fine. You can just write W and W prime. Also no problem. Okay, W1 and W1 prime is fine. Then W2 and W2 prime can, no problem. Okay, losing the first event, winning the second event, losing the both lah, basically losing both. How to get this? 0.3 times 0.7, 0.21. This times this, 0.09. This times this, 0.35. This times this, 0.35. If you total this whole thing, your total probability will be 1. So when it comes to tree diagram, you can check your work. There is no way you can be wrong. Total branches 1, total branches 1, total branches 1. Write down your probabilities. All right, so are we good there? So let's answer the question. What's the probability she wins both events? That means she wins the first and win the second. Win both, 0.21. What's the probability she wins the 100 meter? The 100 meter is which event? Second event, right? So what's the probability she wins second event? Here got win second event, not got, so we can accept this. Here, no. Here got win second event, right? So we can accept this. Here, no. So it's either win both or lose the first and win the second. So, all right. So this plus this. So how do you get 0.56? 0.21 plus 0.35 will give you 0.56. So whenever you go downwards with the tree diagram, you always add. From left to right, you multiply. Downwards, you add. Okay? I have gone through this before. There. This way, multiply. This way, add. We have done it before, okay? In chapter 7. Alright? Next one. You arrive at the pool just in time to see her receive a gold medal for the second event. So second event she won, given this. Given is what? Conditional probability. So what is the condition? The condition is she won the second event. So the condition is she won the second event. What is the probability? She had already won the first event. So what is the probability? She won the first event given she's won the second event. Okay, so if you look at conditional probability formula, the top is W1 and W2. W1 intersection W2, which is this one, 0.21, over W2. That is over the probability of winning the second event, which is this, 0.56. Pause and play, understand slowly, because then you may not be able to understand what am I saying here. Okay, pause and play as you go. You will get 0.375. All right. Next event, next question. Okay, let's bring this here so you'll be able to see what's going on. Okay, just want to, so you'll be able to, all right. So the next example, which is example 4 in your manual, it would be here, all right? Okay. An injection which helps the early detection of TB is known as a Mantoux test. So now, wherever got no numbers, wherever you don't understand, not your problem, don't stress yourself. Before being generally available, this procedure was trialed on a controlled population. Wherever there's a probability, you usually have to use it. So let's highlight it. 0.5% had the disease. The research team found that the Mantoux test returned a positive result with 98% of the people with TB. That means they have TB, come out positive is 0.98. They have also found 95% of the people who are free returned a negative. Okay, so we're going to make use of this information that we have highlighted here. I would like you to do the same. Highlight it. Okay, so we will start with the first part. Okay, the first and the second event, all right? The first part is basically you have TB or you don't have TB. So now you have TB or you don't have TB. That means you have TB or no TB. So I'm using TB and TB prime. TB prime means no TB. So here basically what's happening, I'm telling you here, you know, it's the test going on. Okay, so what is the probability? Maybe I just don't want to confuse you. I won't put that there. Okay. So what is the probability that they have TB? 0.5% have TB. So when you change 0.5% into probability 0.5 over 100, you will get 0.005. So if 0.005 got TB, 1 minus this is 0.995, no TB. All clear there? Okay, 0.5% have the disease, don't have will be 0.995. Then the research team found that the test returned a positive result in 98% of the people with TB. Meaning if I have TB, the result is positive is 0.98, negative 0.02. Okay, so this one total is 1, this one total is 1, you're on the right track. They also found 95% who are free of TB, that means don't have TB, return a negative result. Don't have TB, returned a negative result 0.95. Do you see that? So this one will be 0.05, total 1. So write out your outcome. Have TB, come out with positive. Have TB, come out with negative. Have no TB, come out with positive. No TB, come out with negative. Okay, find the probability that a randomly chosen from this population returned a positive result to the test. So before we do all that, write out your probabilities one by one. So how to find it? This times this gives this. This times this gives this. No TB and positive will be this. No TB and negative would be this. So once you already write down all your probabilities, I would suggest that you add all of it up to see whether you get a total of 1, and you pretty much know you're on the right track. So return a positive result, meaning you need to find all the outcomes that have a positive result, is the one that I've highlighted for you, these two. So you take both the values, you add it up, and that will be the answer. Had the disease if they returned a positive result. This is when it is conditional probability. When you see a phrase like this, if they return, this is condition, given that they return a positive result. So that is your condition. So this is your condition. So given that they returned a positive result, what is the probability they had the disease? So had the disease, given positive, okay, or I would say had TB would be easier for you to understand. So your formula, according to what we have learned, the top should be the intersection of these two, which will be 0.0049. That means they had TB and positive, and the bottom is the total of it being positive. We have calculated here. You divide it, you will get this answer. Okay, after a week of trials, there were 1015 people with positive results. Using the solution from here, how many of these would you expect to have TB? So you just take 1015 times the probability, round off to a nearest whole number, you'll get 91. Okay, I know it's a little complicated. I know it's a bit difficult. When you look at it, you go, I don't know how to actually approach the question, but you will get used to it. Okay, you will get used to it. You have to get used to it. Okay, read the question slowly, highlight whatever that you need to, basically wherever you need to use the answers. Okay, so this is exercise 8.3, which is what we're going to do today. All right, we're going to do this basically. So these are the answers for it. I'll suggest that you pause here. We are only going to do question 1 to question 10. So we will do 10 questions every time, which will be easier for you. All right, so we will do exercise 8.3. I wanted to only do 10 questions, but I think we can finish all 14. All right, so we will just do exercise 8.3 for today's class. Okay, so pause it here if you want to check the answers. I'll go through the questions. Okay, there are 5 M&Ms left in the box, 3 green, 1 yellow, 1 blue. You first ate one and then ate the other. So this is similar to what we did the example in chapter 7's tree diagram. Okay, so you draw out the tree diagram first. Okay, so you branch out first, green, that means you can just call it G, Y, B. Then you branch out 3 again, G, Y, B. So the first pick, it will be 3 out of 5 for green, 1 out of 5 for yellow, and 1 out of 5 for blue. Okay, in the second pick, it will be out of 4. I've taught you this before, so I really hope you're able to manage it. If you can do it without drawing, also I'm fine. Okay, maybe some of you are able to see it without drawing the diagram. I'll show you one example. Actually, you can do it without drawing the diagram. What's the probability you get a blue one followed by a green one? So if the first one is blue, what's the probability the first one is blue? There are 5, right? 1 out of 5, correct? Times the second one is green. So if I'm already talking about second now, it has to be out of 4, right? So if the first one was a blue, you didn't pick a blue in the first. So green still got 3. 3 out of 4. That would be your answer. You understand? If you can do like that, go ahead. But if you need to draw and see, please draw and do it. Okay, I do a second one. A blue one followed by a green one. A blue one followed by a green one. So the first big blue should be 1 out of 5, correct? Times green. Followed by a yellow one. So yellow should be 1 followed by a yellow one, right? So it should be 1 out of 4. Second pick will be out of 4 already. All right? 2 green ones. So first pick, there are 3 greens, right? 3 out of 5. Correct? Times with. Now, initially there were 3 greens. You've already picked out 1. So you're left with 2 greens out of 4. So if you actually can't see what I'm doing, please draw the diagram. It will be very clear. So blue one, the 2 blue ones. Is there a probability to get 2 blue ones? Let's see. First one is 1 out of 5. Right? 1 blue out of 5. Times with blue finish, right? Can you get another blue? No, it will be 0. Not possible. So this probability will be 0. Not possible to get 2 blue ones because there was only 1 blue one in the box. A yellow followed by a blue. So a yellow followed by a blue. What's the probability of getting a yellow? 1 out of 5. What's the probability of getting a blue? Blue also 1 out of 4. So if you cannot see what I'm doing, just draw the diagram. Which of the 2 most likely would you have eaten? So if you've drawn the whole diagram, write out all the outcomes, write out all the probability, you'll choose the one with the highest probability. Okay, most likely is always highest probability. Okay, 2 cards are dealt from the top. So this one I already told you in chapter 6, you must know the deck of cards well already. Okay, how many cards are there in one deck? 52. All right, calculate the probability. The first is a king and the second is A. Okay, the 2 cards are dealt from the top of a well shuffled pack, one after the other. All right. All right, so the first is a king. So how many kings do you have in a deck of cards? 4 kings, right? Out of 52 cards. You times with. The second is an ace. So what's the probability that the second would be an ace? What's ace? The A. So by now you must know the deck of cards. If not, you won't be able to answer certain probability question. So how many A's do you have in a deck? You still have 4 because the first one taken out was a king, right? But now it'd be out of 51. All right, out of 51. Why? Because you've taken out 1 card from the deck. So you'll reduce by 1. All right, so you multiply that, you will get 4 out of 663. So the probability of getting the first king and the second is an ace is 4 out of 663. That means the probability is quite small. Okay, the first is a club. The club is the shape. Okay, how many clubs do you have? You have 13 clubs. And the second is a heart. How many hearts? Shapes is 13 of each shape. All right, so the first is a club. What's the probability? The first is a club, 13 out of 52. Multiply with the second is a heart. All right, there are 13 hearts out of 51. So you multiply, you will get the answer. The first is a club and so is the second, meaning you take 2 clubs. 13 out of 52. Club is the shape. If you don't understand, go back to chapter 6. I have put out the whole diagram there. Go and look at what's a deck of cards. All right, so you will know what I'm talking about. And the second is also a club. So if you have taken out 1 out of the 13, you will be left with 12 out of 51. Okay, moving on. Question 3 is very much similar. A bag, 4 red and 6 black. 2 beads are chosen at random, one after the other. First bead is put on the table before the second. So this is dependent, meaning similar to the first one. Okay, if you need to draw it and then answer the question. If you can answer without drawing, all the better, no problem. Okay, for random events, this find x intersection y. You can find. Why? Because you can use this formula. Why? How to come up with this formula? Okay, you use your conditional probability formula. This would be y intersection x and x intersection y is the same thing. Okay, so if this formula, if you open it up, that means you're using your conditional probability formula, y intersection x over x. All right, so I'll just show you one actually. Okay, I will show you the first example. So we have basic, okay, I'll change this so you can understand what's going on. All right, so let's say this is y given x. All right, so the top should be y intersection x over x, correct or not? Okay, so now what should be the top? Y intersection x. So basically, okay, I'll just show it to you on the bottom. All right, okay, so you have y given x here, which is 0.2 from the first part. Y intersection x, you don't know. Y intersection x or x intersection y is the same thing. Total of x is 0.9, correct? So basically, what is y intersection x? 0.9 times 0.2, which is 0.18. So in this, for the first part, the answer should be 0. So y intersection x will be 0.18. So you do the same thing for B, C, and D, you should be able to get answer. All right? Okay? Okay, so that's how you do number 4. Number 5, if it is cloudy in Albany in July, the probability that it rains is 0.93. In Albany in July, 24 out of 31 is cloudy. So this is basically, when you see if and all that, it would be a tree diagram. So cloudy, not cloudy. So 24 out of 31 is cloudy. 7 out of 31 would be not cloudy. Okay? If it is cloudy, the probability that it rains, that means cloudy, it will rain, not rain, will be 0.93. Not rain, 0. So you draw the tree diagram and try to answer the question. Okay, just try. You should be able to get it. Okay, you can actually skip question 6 and 7. If you want, you can try it on your own. It's no longer applicable to you, but if you want, you can try it on your own and check the answer, which is in the slides I showed you all earlier. All right, you can try it on your own. Okay, number 8, a new test for disease is not foolproof. Okay, it's not foolproof. In fact, 8% of the people who do not have the disease test positive. In the population as a whole, 1 person in 4,000 is believed to have the disease. So this is similar to the example I did with you. So now I want you to read it on your own and try. So you have 1 out of 4,000. So highlight these kind of things. Have the disease. That means it starts with have the disease, don't have the disease. Have the disease, 1 out of 4,000. Don't have, 3,999 out of 4,000. Okay, then you have positive, negative. 8% of the people who do not have the disease test positive. So don't have the disease, positive is 0.08, negative 0.92. All right, so the top part, they didn't give you the information. It's okay, don't draw it if you can't. So try first. Okay, the person will not have the disease, the person will not have the disease and will test positive. So you should be able to manage this. Okay, number 9, for each pitch in a baseball game, a batter has an 80% chance of hitting the ball. So hit is 80%, don't hit is 20%. If he hits, that means foul, not foul. So you got to draw your tree diagram. I don't want to really help you through all of it, because then when it comes to other questions, you will be quite dependent. I want you to learn, think, highlight things like that. So 80% chance of hitting the ball. That means H is 0.8, H prime will be 0.2. If he hits the ball, that means if H, after H it branch out again, right? Got F, that means foul, and F prime, no foul. So if foul is 5%, 0.05, F prime will be 0.95. That's how you manage it, okay? All right, so from that, draw the diagram. Which information they didn't give you, don't crack your head. It's probably just not there. Doesn't mean all the time it has to keep branching out, okay? Again, we are talking about cards here. 2 cards are drawn at random from a standard pack. The first card is not replaced before the second is drawn. The first is a heart. Okay, I'll do this with you. The first is a heart and the second is a diamond. So the first is a heart, 13 out of 52. times diamond. Diamond we didn't touch, right? 13 out of 51. Okay, the second one. The first is a diamond. The first is a diamond and the second is a heart. The first is a diamond, 13 out of 52 times 13 out of 51 will be the same thing, isn't it? One is a heart and the other is a diamond. What does this mean? They didn't give you the order. Like here they gave you the order, which is first, which is second. Here they didn't give you the order. They said, so it can be any order. So what would be your outcome? Either the first is a heart and the second is a diamond. The word is a big or the first is a diamond and the second is a heart. So you will take these two answers and you will add it up. So your answer will be the addition of part A plus part B. Okay, that's how you get it. When they don't give you the order, you have to take both the orders. If they give you the order, you follow. They don't, it can be either this first or this. So when it's or, you add it up. Alright, two randomly chosen letters are crossed out from the word distance. Calculate the probability that they will both be consonants. So these are all simple. Do it slowly. How many consonants, how many vowels? The first will be a consonant and the second will be a vowel. Okay, and you multiply. The first is a consonant, so you basically find the probability the first one is a consonant times the second one is a vowel. All right, crossed out means it is dependent. That means, okay, now how many letters you have here? 1 2 3 4 5 6 7 8. So what's the probability? They will both be consonants. So if the first one being a consonant, it will be out of 8. The second one will be out of 7. Understand? This also first one out of 8, second one out of 7. So same goes to this. Okay, one will be a consonant and the other will be a vowel. They didn't give you the order. So it can be first consonant then vowel or first vowel then consonant. So you need to add it up. Okay, this one, a large chain store company finds that 70% of the items sold are less than 50. Also, only 20% of the items are paid by credit card. If it's costing more than 50, 60% are paid by credit card. So this will be a tree diagram. I want you to try and draw that. If there's, whenever you see if there's events one after the other, it's always a tree diagram. So I want you to try and draw the tree diagram first, if you can, on your own. Okay, determine the probability that the next item sold by this company is not paid by credit card. So you can only get the answer once you have drawn the tree diagram. So it will start with less than 50, more than 50. After that, paid with credit card, that means C, C prime, C, C prime. Understand? And write down the probabilities. All right, the weather in Melbourne is difficult to predict in autumn. On average, 3 out of 4 are fine. If it is fine, this is also a tree diagram. So F prime, fine, not fine. 3 out of 4 is fine, 1 out of 4 is not fine. If it's fine, 60% chance it will be fine in the afternoon. So fine again in the afternoon. So maybe the fine in the morning, you can call it F1. Fine in the afternoon, you can call it F2. It's up to you how you call it, totally up to you. Draw the tree diagram and try and answer the questions. All right. A tennis player is allowed 2 serves. The probability that a particular player gets a first serve in is 0.6. This is also a tree diagram. If she gets a first serve in, the probability that she wins a point is 0.8. So this is also a tree diagram. I would want you to draw it, answer the question and try it on your own first. Okay, so we will stop here today. If you cannot manage on drawing it, don't worry, I'll be drawing all the diagrams and sharing it in the channel. So no worries about that, okay? So, but you try it on your own first, then I will draw and share it. Okay, so we will stop here. Once you're done, any questions, just reach out. I totally understand that this topic is a little bit difficult. You may not be able to understand the questions, but just try. Read it slowly, highlight and try.